on how it's made. Dress forms. We'll show you the bodybuilding techniques. Boat propellers. We'll bring you up to speed on how they're made. Duvets. Get down. And faucets. We go to the factory where they do a plum job. When it comes to dressmaking, a dummy can be a lot of help. These dummies are known as dress forms, and they're full-scale duplicates of the human body. They give the sewer a form on which to solve fitting problems. They're also used to showcase outfits in storefronts, where they look pretty smart, all dressed up. For centuries, the fashion industry has relied on dummies to act as stand-ins for clients so they don't have to endure lengthy fittings. Sometimes a form is even custom-made as the client's exact body double. To make one of these forms, a worker soaks cardboard in water. It's strong and porous, so it can absorb a lot of water without falling apart. He positions the back half of a plaster body mold, and then he rips a soaked cardboard sheet in two. He dips his gloved hand in paste and slathers it on the cardboard. This paste is a combination of plaster and tacky glue. He makes a series of tears along the edge of the cardboard. It's a technique called feathering. He presses the glue-coated cardboard into the shape of the body mold, building up several layers. He arranges some pieces lengthwise and others horizontally for a tight interweave. And he overlaps the feathered edges to interlock them. He taps them with a hammer to make them level, then lifts up some pieces at the center. Now he joins the front of the body to the back. The cardboard forms fit loosely on top of one another. To interconnect them, he uses more paste. He manipulates the end of a paste-covered tool inside the cavity, overlapping loose layers with the adhesive. He opens the mold to reveal the shape. This dummy is a North American size 12. That's size 10 in Europe. After 24 hours of drying in the open air, the form goes into an oven where it bakes for 8 hours at 177 degrees Celsius. This causes the moisture to evaporate from the form, hardening it. An employee scrapes off all the rough bits with a rasp. And then he sands it smooth. Next, an employee draws lines on the form with a pencil. He'll use these marks as guides as he cuts into the dress form to make the shoulders collapsible. He carves out slots on each side of the form and then peels back layers on either side of the slots. This allows him to install hinges level to the form so they won't protrude and ruin a fitting job. The dress form then undergoes some major surgery. He slices open both shoulders, but leaves them attached to the rest of the form by the hinges. He checks the function of the hinges. Then trims the dress form along the incisions. This will allow the shoulders to be tucked into the form in a collapsing posture, a feature that will make it easy to pull a garment over it. This piece of pliable steel is a spring for a mechanism that locks the collapsed shoulders in position. He attaches it along with the rest of the locking mechanism to wooden supports in each shoulder. It's time to pull back those shoulders and show off that adjustable profile. The dress form is now covered in layers of jersey and linen. These pins will serve as reference points for the sewer. Another worker then washes this dress form with a wet sponge, shrinking the fabric to the form. this dress form gets the stamp of approval. A worker then gives the headless body a metal collar and caps it off with a gold-colored finial. And now you have a body shape that's made to measure. Boat propellers were invented in the early 19th century, and they've been making waves ever since. These propellers rotate in a screw-like fashion, drawing water in and pushing it out to move the boat across the water. It's why the propeller is sometimes called the screw. With a steel propeller, you can skim across the lake in a flash and a splash. To make a propeller, they start by melting wax pellets until they're the consistency of toothpaste. Nearby, a mold of a boat propeller closes, and they inject the thick wax into it. It takes about a minute for the wax to cool into the propeller shape, which will serve as a pattern for making the metal prop. A bit of compressed air helps extract a wax funnel from its mold. It's called the pour cup. We'll see what it's for later. They wipe down the cast shapes, then soften the end of the prop on a burner and join it to the glue-coated end of the pour cup. They dip the attached pieces into hot wax to fill any gaps in the joint. A quick wash and rinse gets rid of any oily residues on the wax models. Here, a robot submerges a rack with several propellers on it in a special solution that gives them a non-stick coating. Then it's over to a tank that contains a mix of silica sand and water. The robot dips the wax propellers in it several times, then plunges them repeatedly in ceramic-based concoctions. After each dipping, the propellers go into a machine that showers them with sand. Then they dry in a room with a system of fans. The process of dipping and sand bathing builds up a hard ceramic shell around the wax. They load the propellers into a pressurized oven called an autoclave, where the wax melts away, leaving only the ceramic shells. They fire those ceramic shells in big ovens, the way potters bake ceramics to strengthen them. Nearby, molten steel is bubbling, heated to the melting point by electrical induction coils. They take a ceramic propeller shell out of the oven and pour the searing steel into it through the pour cup. The steel immediately begins to cool, causing cracks in the ceramic shell. They knock off the remaining bits of ceramic. When they make these steel propellers, they really throw away the mold. Next, they cut off the molded pour cup because it's no longer needed. They grind the edges to smooth them. Then, a more intensive grinding removes any corrosion on the surface. This takes skill and strength. Talk about putting your shoulder to the wheel. They lower the propellers into a series of vibrating polishers. The friction from these pulsating cones smooths out the grind lines on the propellers and adds shine. Finally, each propeller gets the once-over from a laser that measures the blades from all angles. It sends the information to a computer, which compares it to the specifications. If it checks out, the propeller will be on its way to a waterway for the big launch.
The future is in the city.
We live in cities now as a species, and there's no going back.
Experts weigh in on one of the world's youngest global cities.
Singapore is now at a crossroads. It's at a real turning point.
A search for the hidden design and soul that makes a city livable.
This is a typical Singaporean breakfast.
Living Cities, Singapore, a 6-part series. Premieres Wednesday, 15th of December, exclusive to Discovery Channel.
Oh, this, trust me, this is the invitation of a lifetime, yeah? 2 people get the chance to win a trip to London. Woo! And there's lots of Canon goodies to be won as well. Plus, and this is the best part, come a bit closer, yeah? You get to meet me for a whole afternoon. Woo! Yeah, yeah! Well, I thought it was quite a good prize myself. But anyway, if you want to know more details, then log on to the following website.
Canon, delighting you always.
They do it tonight on Discovery Channel. Big just got bigger. Mega structures of epic proportions, pushing science and technology further than ever before.
Look good. Beautiful thing.
Modern engineering at its awe-inspiring best. Mega Builders. Tomorrow night on Discovery Channel. Programs that had you on the edge of your seats. That amazed you. Thrilled you. And inspired you. We experience, relive the best of Discovery. 13th to 19th of December on Discovery Channel.
Down is the term for belly feathers of waterfowl, primarily ducks and geese. Down is made up of interlocking fibers that create micro-sized air pockets. These work something like a scuba diver's wetsuit. The bird's body heat warms the trapped air. The warm air then insulates the bird against the cold water. Feathers have a central stem from which the fibers emanate. Down is more lightweight and its fibers are in clusters. Bags of plumage from waterfowl farms arrive at the feather and down processing factory. The first step is to separate the down from the feathers. A vacuum hose sucks everything up into a sorting machine that has 4 air chambers side by side. In the first one, the air blows everything upward. The heaviest feathers rise just part way, while the lighter plumage floats through an opening into the next chamber. Same air sorting process there. Heaviest stays, lighter moves on. This continues until there's only pure down in the 4th and final chamber. A vacuum hose transfers it to the cleaning machines. First, agitation and suction remove any dirt trapped inside the fibers. Then, a 13-cycle hot water wash with soap to kill bacteria, and degreaser to strip the natural oils that coat the down fibers. The last rinse cycle applies an antibacterial antifungal treatment. The next machine spins the down to remove the water. When the down comes out, it's still a bit damp. A robotic machine called the picker gathers small batches at a time and loads them into a steam dryer. After processing, the factory's lab tests a sample from each batch for cleanliness. Technicians also evaluate loft, the technical term for filling power. The higher the loft, the better the down will insulate. They measure how much space the sample fills. If the down meets specifications, the factory bags the batch for shipping to the duvet factory. First stop there, a holding tank. A programmable filling machine extracts a specific amount of down and transfers it to a canister. They shoot the canister's contents into a duvet's fabric shell. To keep the down evenly distributed throughout the duvet, they've sewn the shell into sections called boxes. Emptying one tube at a time, they fill one box at a time. That down portion stays within the box's fabric walls. Of course, that air pressure piles it all at one end of the box, but they'll spread it out later. They close the open end of each row temporarily with a plastic clip. Once they've filled all the rows, the duvet goes off to the sewing department. There, seamstresses stitch the open ends closed and sew on labels and washing instructions. A light table allows them to see the down within each box. Then they spread it out evenly using, of all things, badminton rackets. The fabric shell is 100% cotton that went through a high-pressure treatment to fuse its fibers so tightly that no down fibers can poke through. The factory also stuffs bedding items with feathers. Back at the processing factory, feathers go through the same post-washing tests that down undergoes. To measure cleanliness, lab technicians soak a sample from each batch in distilled water. Then they strain the water, mix it with sulfuric acid, then add a potassium compound. Then they analyze the color of the liquid to gauge its oxygen content. If the oxygen level's under 10, the feathers are clean enough to ship to the duvet factory. There, the feather filling process is just like the down filling process, only with bigger canisters and blowing nozzles to accommodate the larger feathers and larger fabric shells to stuff. Feathers are heavier than down and have less insulating power, but they're more affordable. Down covers only the bird's belly, and that scarcity makes it expensive. That explains why high-end bedding contains 100% down, while the rest contains either a down and feather mix or feathers alone. But there's no downside to any of those options when it comes to getting a cozy night's sleep.
Every day holds promises and challenges to be met. At the BNP Paribas Group, we understand it takes everyone to move the world forward. So let's keep trying, let's keep dreaming, let's keep reaching. BNP Paribas, the bank for a changing world.
Completely yours. Soul.
The real voyage of discovery is not necessarily seeking out new landscapes. It's more seeing it with new eyes.
A world of possibilities. Canon, delighting you always. Bear Grylls has a new mission, putting himself into the real-life scenarios you fear most and finding the smartest ways to get out alive. Worst case scenario, tonight on Discovery Channel.
People, if they dare, then have me, all of me, in their homes. Even dressed like this. It's not aggressive, is it? They would get it afterwards. Obviously, you don't want me in your house. Bollywood, it's only big for one star, and that's me. Stay down! Stay down! Obviously, I've got to be invited.
Open your doors and invite Mr. Right, a new series. Premieres Tuesday, 14th of December on TLC.
Programs that had you on the edge of your seat. That amazed you. Thrilled you. And inspired you. Re-experience, relive the best of Discovery. 13th to 19th of December on Discovery Channel.
Faucets were actually invented by the ancient Romans. But when their empire collapsed, so did their water and sewer systems. It took many centuries for running water to make a comeback and for water to become available on tap. But today, faucets help us all lead cleaner lives. Modern faucets are designed to work well under pressure, as in water pressure. They start by setting a brass spout tube on a revolving support. An automated dispenser applies silver solder to the inside rim of the spout. They press a threaded tip into the spout, then dip the other end of the tubes in flux paste, which cleans the brass and prevents tarnishing. They set the tubes against brass hubs. Then torches liquefy the solder, which flows into the joint, sealing the tube to the hub. The threaded tip is soldered in turn. A carriage now moves the faucet spouts against buffing wheels, coated with polishing compound for a mirror finish. A wheel with an abrasive surface gives that finish a brushed texture. They dip the faucet spouts in an acid bath laced with dissolved nickel. They apply an electric current, which draws the dissolved nickel onto the brass spouts, plating them with a thin, even layer. Next, they load the faucet spouts into a special chamber. Inside, an electron beam flashes like lightning as it spirals around a zirconium rod. This causes the zirconium to vaporize. The vapors mix with gases being pumped into the chamber and bond to the faucets for a final finish that's virtually indestructible. They give other parts of the faucets the same coating using the same process. Meanwhile, a blade slices a solid brass rod into smaller pieces. A variety of cutting tools machine the brass lump to make a faucet body. It will house a ball valve that controls the volume and temperature of the water. A jaw grabs the other end of the brass body to position it for more drilling. Several tools carve out holes that will act as waterways. The waste brass gets recycled. That piece of solid brass has been transformed into a pivotal piece for the faucet, the valve body. With copper tubes and brass fittings now attached, they slide the faucet into the base plate. That's the plate that sits on the sink deck. They fasten it with screws, working from underneath. Next, a robot puts one half of a stainless steel ball in a spinning vise, which properly orients it so an automated welder can join it to the other half. The ball's openings align with hot and cold inlets in the faucet body to regulate the flow of water into the spout. They insert rubber seals in those inlet holes in the faucet body. Rubber O-rings on the body will both form a seal and allow the spout to swivel. In goes the ball valve. Then they cap it with a rubber seal. They screw the aerator onto the spout and tighten it with a pneumatic driver. Now they secure the spout assembly to the rest of the faucet with a metal bonnet. It's time to see how this faucet runs. They connect it to a pressurized water source and check how it functions. Finally, they attach the handle to the rest of the faucet and it's ready to ship out. They include the spray hose and support system. Those are to be installed on site. It takes a day or two to build one of these faucets, but it will be on cleanup duty for many years.